Today's lesson is on optimizing in 3-dimension. So remember when we talked about optimizing in 2-dimension, and we said we wanted a rectangle that had the maximum area for the minimum perimeter, we would have a square. So likewise, if we're in 3-dimension and we want a rectangular prism to have maximum volume and minimal surface area, a cube would be the thing that does it. So let's just label our cube. We have our length, width, and height. And because this is a cube, we would have the length is equal to the width and equal to the height. So let's use example 1 here. You're constructing a rectangular prism with maximal volume using exactly 384 inches squared of cardboard. Which variable is fixed? Now you see that this is inches squared. And when we have a unit that is inches squared, we know that it is an area because this is in 2-dimension. It's not volume because volume would be cubed. So I know that surface area is fixed. So what's the dimension of the prism? Okay, let's have our volume. Our volume equation, because we know that length times width times the height is the same, I could say this is going to be side cubed. For surface area, I have 6 sides that are exactly the same. So I'm going to have 6 times s cubed. So let's take this and I'm going to substitute this into my surface area equation. 384 is equal to 6 side squared. 384 divided by 6 is equal to 6 squared, or s squared. And then we have the square root of 64 is equal to s, and s is equal to 8. Okay, so we know that this shape has to have 8 times 8 times 8. So what's the volume? 8 to the power of 3, and we have 512 inches cubed, or cubic inches. Okay, let's do another example of this. Basil constructs a rectangular prism that must have a volume of 1,331 meters cubed and a minimal surface area. What is fixed here? Is it volume or surface area? So our constraint is the volume. Volume must be 1,331. So what's the dimension of the prism that has the least surface area? So we know that a cube is the rectangular prism that has the maximal volume and minimal surface area. So because that's the case, let's write our equation. Where volume is 1,331 and volume is also side cubed. So for us to find the side, we're going to take the third root of 1331. And then we get S is equal to 11. So this prism is going to be a cube with the side length of 11. So what's the surface area of this? My cube is going to be, it's going to have 6 sides that are exactly the same. So my surface area is 6 times S squared. Surface area is equal to 6 times 11 squared. And we have 726 meters squared. So once again, I'm just going to give a reminder, be very sure what units you're in. Surface area is 2 dimensions, so we have meters squared here. Okay, slide number 4, I'm going to pause to let you try this on your own. Okay, so let's take these up. The first one, we had the side length of 4, and so our volume would be 64 centimeters cubed. The second question, we're given the volume. We know that the volume is equal to 125,000 meters cubed, but we also know that the volume of a cube is going to be side cubed. So I can equate these two. I have S cubed is equal to 125,000. Let's take the cube root of this. And we have side is equal to 50 meters. So surface area is equal to 6S cubed. It's not asking us for the surface area, but we can tell them the dimension as was asked. What's the dimension of the box? Okay, let's go on to the next example here. We have a glass vase. You're designing a glass vase, and it's going to be a rectangular prism with an outer surface area of 225 centimeters squared. One thing I do know is that the surface area is fixed. They've told us that. We also know that a glass vase is only going to have 5 sides instead of 4. Because if it's the vase, for it to be useful, I need to have the top part open so that I could put flowers in here. Before I solve any of the questions, I'm just going to draw a diagram, the net diagram of this, so that it becomes clear what we have. Okay, this is reasonable enough, I think. So we've got our 4 sides and we've got the bottom. This is a net diagram of this vase. Determine the maximum volume of the vase. Okay, for the vase, we know that we're going to have length times width times height. So let's label this. Oh, and one thing I should have mentioned in the question is that this is going to be a square-based prism. All right, so sorry about that. I needed to put that in the question. So because this is a square-based phase, the length will equal the width. Since length is equal to width, let's use the variable b to represent the base. So my new volume, I'm going to have volume is equal to b squared times h, because length times width is the same as b. So I have b times h. Okay, since I don't know b and I don't know h, I can't substitute those in to find the volume. But I do have this as my given constraint. And since that's given as a constraint, I'm going to write my surface area equation and then substitute this into my volume equation, the same way that we did when we were doing this in 2-dimension. So I'm going to put this in here. So I have base, and then height and base again. So surface area is equal to 4 panels that are identical to this, h times b. And then I'm adding 1 panel that is b squared. I do know also that surface area has to equal 225. So I'm going to substitute that into the equation. 225 is equal to 4hb plus b squared. I'm going to rearrange this for the letter h now. So I could have minus 4hb is equal to b squared minus 225. I'm going to divide both sides by negative 4b. Negative 4b. Okay, and then we can substitute this into the volume equation. So remember, volume is equal to base squared times h. So I'm going to put volume is equal to b squared times b squared minus 225, all divided by negative 4b. Put this into your graphing calculator now to see what your maximum volume is. So remember, y-axis represents volume, and x-axis is our b, which is our base. Let's substitute this in here now. Cutting and pasting, I'm also going to change my b's for x's. And then I need to shrink this so that I can see it. Let's make this Right, so our graph looks a bit like this. But once again, I am not going to take quadrant 2, 3, or 4 into consideration because I can't have a negative volume. I also can't have a negative base. Okay, I've labeled all this. And I find that my maximum value, 8.7 and 324.8. Let's take this back over and interpret our answer now. So because our base length is 8.7, I can substitute this back into this equation to find my height. So we have 8.7 squared minus 225 divided by -4 times 8.7. So height is equal to 4.3. So our dimension of the vase we're going to have a base of 4.3 centimeters by 4.3 by our height of sorry, I made a mistake. The base is 8.7 by 8.7 and the height of 4.3 centimeters. So it's actually going to be a fairly shallow vase, unlike this, but this would be what gives us the maximum volume. In the next slide, I'm going to let you try this on your own. It's very similar to what we did last time. We're writing one equation, rearranging it so that we could stick it into the other equation to solve for the missing dimension. Okay, in this question, we have a large open box, no top, to be shaped as a square-based prism. It has to have a volume of 2,500 centimeters cubed. You want to minimize the material used for the surface area, but you have a fixed volume. Similar to the other question, we now have a fixed volume, but we're going to do the same thing. So once again, I'm going to draw a diagram once I can find my cursor. We have a box and it has a square base. So when I have a square base, I'm going to label my sides. So these are all sides that are the same. And then I have these sides that are also the same. Let's label this. So I'm going to call this side H, and the base, because the length is equal to the width, I'm going to just call this whole thing B. So I have B, B, and B. Now my area surface area for all of these. The base would be b squared. The first panel, h times b. Next one, also h times b. Third one, h times b. Fourth one, h times b. Okay, let's write down the volume and surface area. So what I've written in blue is my surface area. So I've got 4 HBs, so HB plus HB plus HB plus HB plus B squared. So simplified, I have SA is equal to 4HB plus B squared. Now the volume is equal to length times width times height. But we have said that L is equal to W, and we're using the letter B to represent the base. So since we know it's a square, it's going to be B times B. So volume is equal to B times B times B, sorry, B times B times H. So simplified, I have volume is equal to B squared times H. Now I also know that the volume is 2,500 centimeters cubed. So I can rewrite that equation as 2,500 is equal to B squared times H. And I'm going to rewrite it again so that I can express it with only one variable. So I have H is equal to 2,500 over B squared. Now that I have this, that's the constraint that I have to work with. So I'm going to substitute H into the surface area equation. So surface area is equal to 4 times 2,500 divided by B squared times B plus B squared. So this is a bit of a mess, but I'm going to put this into a graphing calculator, and that kind of solves my problem. So for graphing, y-axis is surface area, and x-axis is B, base length of square bottom. Let's take this equation, and I'm going to plop it into our graphing calculator. Okay, we have to substitute it with x and y's now. I'm also going to change the values of my x and y axis. I know that x-axis is the base length, y is the surface area. So let's find our value. Minimum value is 17.1. And the other coordinate, 877.2. So we come back here and we find that this is the minimum value. That means that the base has to have the length of 17.1, and I can substitute it back in here to find my height. So base is this, height is equal to 2,500 divided by 17.1 squared. Okay, our height, 8.5. Okay, so dimension of the box. 17.1 centimeters by 17.1 by 8.5. I'll give you a moment to take this down, and then we'll go on to our next example. Okay, the last example that we have, we're an industrial designer and you've been asked to design a cylindrical can that holds 350 milliliters of fluid with the least amount of aluminum possible. So let's just first do the conversion. 1 centimeter cubed is equal to 1 milliliter. That means the volume that we're working with is 350 centimeters cubed. Right, for my container, this is a very rough drawing, but I have my height, and the other dimension that concerns me is the radius. Okay, so let's write our equation. Volume is equal to pi r squared times h, and surface area of a cylinder, we can open it up. We would have 2 circles on the top. Circle on the top and circle on the bottom. This is our height, and we still have our radius there. This would be the circumference. So surface area, we have 2 pi r times h, that's our rectangular piece here, and then 2 circles, pi r squared. Find the dimension of the can that has the minimal surface area. Okay, let's rewrite our volume equation. We know that volume is 350, but it's also equal to pi r squared times h. Let me express this as an equation of h with the variable r. So we have 350 divided by pi r squared. So we can substitute h into the surface area equation now. So surface area is equal to 2 pi r times h, which is 350 times pi r squared, plus 2 pi r squared. Let's throw this into our graphing calculator, and then we'll see what the minimum area we're given. Before we do that, let me remind us that our y-axis is surface area, and x-axis is our r for radius. So let me stick this in here, and I'm going to change my variables. Okay. Y-axis, my surface area, let me go up to maybe 1,000. Okay, so we've got our graph here. We have a minimum value of 3.8 and 274.9. .8, 274.9. So when we come back here, we know that the radius that will produce the can that has the least amount of surface area will be one that has a radius of 3.8. I'm going to put it back into my height so that I can find the height of this shape as well. So h is equal to 350 divided by pi times 3.8 squared. So my height rounded 7.7 centimeters. Right, now we have the dimension. The cylinder with the minimum surface area to hold a 350 milliliter drink is 7.7 centimeters high with a radius of 3.8 centimeters. So once again, what we did here, we wrote the equation that we have our constraint for, and then we wrote our second equation. Then we rearranged it and substituted it in for our second equation. We put it into our graphing calculator to see what was the maximum or minimum, and then we solved for the missing variable. Then we have the whole dimension.